And there will be times where we have to use the definition of the limit, times when it makes more sense to use the theorems that we have to compute the limits or to prove the existence of the limit. It really depends. Let's take a look at a few examples. Let's say you have the function f from R into R, which maps every x to a constant value k. The limit of the function of x goes to c, for any c, a limit point of R, any c. Use either one of the approaches here. Let's just do it with the definition. Let epsilon be greater than 0. We can find delta epsilon greater than 0. In particular, the delta epsilon that will work in this case will be epsilon, such that whenever x minus c is strictly greater than 0, absolute value smaller than delta epsilon, and x belongs to the domain, x belongs to R. So I'm not going to specify it here because we've assumed, we write it like this, that x does belong to R, then f at x minus the candidate for the limit k is equal to k minus k to 0, which is smaller. In fact, we could have picked a bunch of other epsilons here. This is always going to give us 0 as long as the delta epsilon is somewhat related to the epsilon. So you'll get what happens if you have the identity function, which associates to each x limit for every c in R going to be c. Can we show that? Let's use the definition. Let epsilon be greater than 0. Set delta epsilon be equal to epsilon. Then, whenever x minus c in absolute value is larger than 0 and smaller than delta epsilon, which we said epsilon in this case, we have f at x minus the candidate L, x minus c. Alright, well, x minus c is exactly what we have here, so that's going to be less than delta epsilon. Assumption, we said that this was equal to epsilon, so that f at x minus L is smaller than epsilon. We have, what about this? How would you prove this? Not doing this one here. I want you to think about how you would go about proving this. So you have the following function from R to R, which assigns to every x the following quotient: x cubed plus 2x minus 4 divided by squared plus 1. You limit this function, x goes to 3. Well, you can use a theorem on the properties here. The limit of the numerator when x goes to 3 is the sum of the following limits. I've used various of the sub-results, products, multiplication by a scalar, and on the sums. And that just leads to 3 cubed plus twice 3 minus 4, 37. That's for the numerator. For the denominator, again, do the same principle. The limit when x goes to 3 of x squared plus 1 would be 3 squared 1, which is. Now, if I want to be able to say that the limit of this quotient is equal to the quotient of the limits, it is not sufficient that the limit here be different from 0, which it is, it's equal to 10. I have to make sure that the value of the denominator is always different for 0 in the domain of the function, which happens to be full. So this is important, right? It's not just the fact that 10 is different from 0, which allows us to say that the limit is 37 over 10. It is the fact that the denominator never takes on the value 0. That is one of the assumptions of the theorem. In practice, what we really care about is that in some neighborhood, the limit point, the function doesn't take on the value 0. But that's not the way the theorem has been stated. Here's an instance where you cannot use this theorem. Compute the limit. It's the limit when x goes to 0 of x squared cosine 1 over x. Like, you'd like to be able to say, oh, that's easy, that's the limit when x goes to 0 of x squared times the limit when x goes to 0 of cosine 1 over x. But whereas this limit here is 0, this limit does not actually exist. How do we prove that? Well, we're going to take two subsequences here. Subsets of R, they each go to 0. None of them are equal to 0. And none of them are equal to 0. These are the sequence that I will pick. 1 over 2n minus 1 pi for xn, and 1 over 2n pi for y. So you agree, there are sequences in R, they both go to 0, and never equal to 0. Note that the cosine of 1 over xn is always equal to the cosine of 2n minus 1 pi, 1 over 2n minus 1 pi, and that's always equal to minus 1, whereas the cosine of 1 over yn is the cosine of 2n pi, always equal to 1. So the cosine of 1 divided by xn goes to minus 1 when n goes to infinity, and this one goes to 1. Two sequences going to 0, leading to the cosine of 1 over these sequences going to different values, and hence this limit does not exist. Now, the fact that the limit here does not exist does not mean that the full limit doesn't exist. In fact, we've seen that this limit exists and it is equal to 0. All this says is that if you want to compute the limit of x squared cosine of 1 over x when x goes to 0, you cannot use the theorem that tells you that the limit of a product is the product of the limits. This is only valid when each of the constituent components has a limit. Now, you might have noticed, though we're more or less following what's happened with sequences. One of the things we did know about sequences is that if the limit of a sequence existed, then the sequence was bounded. Well, the equivalent result for functions is that if the limit exists at a given point, then the function has to be bounded in a neighborhood of that. So A is some subset of R, that F is a function from A to R, and that C is a limit point. So that F is bounded on some neighborhood of C, if you can find the delta positive and a constant m also positive, such that the value of the function in absolute value is smaller than or equal to m for every x. The intersection of A with the neighborhood. I'm getting tired of writing C as the limit point of A, so I'm going to switch to this notation here. C is a limit point of C is in the closure. Here's theorem. Convergence of the limit equals boundedness of the function. Okay, subset of R, F from A to R, C, a limit point of A. So then, if this limit exists, F is bounded on some neighborhood. And we will show that. Let L be the limit in question. By definition, we have a statement which is going to be true for every epsilon. In particular, it's going to be true for the value epsilon equal to 1. You'll be able to find a delta, which I'm going to denote by delta 1 to remind you that this is the delta that corresponds to the value of epsilon that was specifically given as 1, such that the distance between f at x and L is going to be in absolute value smaller than epsilon, in this case smaller than 1, whenever x belongs to the set A, and in absolute value x minus c will be larger than 0 and smaller than the 1. Now, one of the properties of the absolute value seen is that the absolute value of f at x minus L will be bounded below by the absolute value of f minus the absolute value of L. In particular, this means because f at x minus L is smaller than 1, that f at x in absolute value minus L in absolute value will be smaller than 1, or f at x is smaller than L plus 1 for every x in A within delta 1 of the value C, assuming of course that x is not equal to 0. Now, if C doesn't belong to A, the limit point is not part of the actual set itself. You set M to be L plus 1, absolute value of L plus 1. And you're done. If, on the other hand, C belongs to A, because the limit point could also be part of the set, then you would let the constant M, the bounding constant, be the maximum between either the value of the function at C or this bound that we've found here previously, absolute value of L plus 1. In either case, the absolute value of f at x would be smaller than or equal to M whenever x belongs to A and x minus C is smaller than delta. Why do we need to separate the two cases here? Limit point and A, limit point not in A. Think about this.